Good afternoon, class. Today is October 19th, and so today is the video for October 20th. And so we're going to go over homework 5, the third problem. And before we do that, a little bit of a schedule. So today, and I'm writing down times for the lecture. So this is tomorrow. So today's video will be, homework 5, problem 3, and then we will go over dopant diffusion. Now, what I'm going to do is we're, just like last week, we spent the whole week on oxidation because it's one of the, more difficult derivation-based subjects here. This week we're going to, focus on dopant in diffusion, and so the next lecture for the class on the 22nd will be to finish on dopant diffusion. And the videos may be short because, it's not really a whole lot of material. It's just that I want to devote the whole week to it, and particularly in the chat class to make sure that everyone gets it. And then on the class for the 27th, there will be a review for quiz 2, and then on the 29th, quiz 2. As I've announced previously. All right, so homework 5, problem 3. So I'm not going to put the projector up, but basically I gave you a plot of the concentration. So it's 1 in some arbitrary units, and at T1, it Z, capital Z1, this is Z, is equal to, and you can read it off the chart, it's equal to 0.5 microns. This is oxidation still. And I gave you a couple of curves, the starting of the curves, all right, and there were something like that. So basically, the starting of the curves at T2 and T3, and I asked you to tell me, okay, what were the depths at T2 and T3 based upon those curves? And the way to do the problem is to realize that, again, we've gone through the reaction rate is equal to two things. It's equal to the flux, and it's equal to the reaction, the rate reaction constant times the concentration at Z. And so what I wanted you to do was understand then that Cz, the concentration of oxygen at the depth, at the oxidation depth, is proportional to the absolute value of dC dZ. And that's true for all the curves, because as you can see, it's just, I could write down, well, I'll write it down. It's d over k. So basically, I'm asking you to find out what d over k is, and you can do that because you can plug in here, okay, at T1, you've gone half a micron, and you can read off the chart that Cz is 0.75, whatever those units are. So you can work out that d over k is equal to CZ 0.75 over dc dz. Now to get dc dz, you look at the slope. And the slope is 0.25 over, so that's delta C, okay, 0.25 over 0.5, okay. And so if you work at that, then that's equal to, okay, because that's 1/3 times, because you bring 3 on the top, 1.5. So you have that CZ is equal to 1.5 dC dZ, absolute value. And so for 2, dC dZ, you can read off the chart. All right, I won't bother putting the numbers here because you can read it off the chart. Well, I'll go ahead and do it. Delta C is for 2 is 0.1, and delta Z is 0.5. So that's equal to 0.1 over 0.5, 0.2. And so C Z for time 2 is equal to 1.5 times 0.2, which is equal to 0.3. So what you do is I'll draw it a little better. You draw for 2, this is for T2, keep going, and you know that C at the concentration at the depth from that is equal to 0.3. And so you just read off the chart then 0.3 and 3.5. Okay, so that's the answer. Z at time 2 is 3.5 microns. And the same thing for 3. Okay, you see Z, you get off the chart, and so that's basically 0.05 over 0.5 or 0.1, and so CZ2 is equal to 1.5 times 0.1 or 0.15, and so you take his curve and you go all the way down to 0.15, and then you read off the chart, and basically that's 8.5. So that's the answer. Z3 is 8.5 microns. Okay, so hopefully you were able to walk through this, and this was meant to reinforce your understanding that the oxidation reaction rate is equal to two things. It's equal to the flux of oxygen, which is given by Fick's law, dC dZ, and it's also equal to the rate constant times the concentration at the depth C. So I hope that that problem 3 was useful to you in reinforcing your understanding of how oxidation works and how to calculate depths and things like that. Okay, so onward, and we're now going to do dopant diffusion. And you may have noticed that I sent a note on Canvas yesterday because dopant diffusion is, of course, diffusion just like oxidation. Okay, dopant. I'll call it indiffusion. So basically it's very similar to oxidation in the sense that you have your wafer here, okay, and you flow dopant gas across it. And so if you look at the wafer, okay, here's the edge of the wafer, and basically, okay, so yeah, let's do variables here. For oxidation, So it's a similar problem in the sense that here's the wafer. That's the surface of the wafer drawn outside. And so we have, dopant gas. And we're diffusing it into the wafer. And so it's very similar to oxidation in the sense that both are diffusion processes. Now there are differences. Some are minor and some are not so minor. So I'll make a chart here, dopant diffusion. For oxidation, here first the most minor. For oxidation, we use the Z as the variable. For a dopant diffusion, we're using X, and don't ask me why. So this is X, and this is X equals 0, the surface of the wafer. So that's very minor. For oxidation, we use C, which is the moles O2 per unit volume. The concentration of oxygen was our variable. Okay, whereas for dopant diffusion, we use N, which is dopant atoms per unit volume. Okay, so that's minor. So the variable, the distance variable is Z in oxidation, and it's X in diffusion for no good reason. The quantity we're interested in for oxidation is C, labeled as C, which is the moles of O2 per unit volume, whereas in dopant diffusion it's N, capital N, which is the dopant atoms per unit volume. So those are minor little differences. But then the major difference we'll get to right now. Well, I'll draw them. Okay, so for dopant diffusion, C goes like that, as we just discussed. It's a straight line. And also, it's at a given. Okay, so. For a given time, it can be approximately independent of time, and I'll explain that in a minute. Now, of course, C is not independent of time because as time goes on, all right, it does this. But we'll show you in a minute that those curves are the result of the fact that the diffusion of oxygen into the wafer behaves much differently than as we see now for dopant diffusion. All right. For dopant diffusion, okay, it does this. So here it's linear, and here it is not linear. Okay, and we'll show you why in a second. All right, so diffusion. All right, when we covered oxidation, we sort of just brushed over. I mean, we introduced Fick's law, right? Which is that the flux of O2 molecules was given by the derivative. All right. But we just sort of like swept the rust under the rug. We said, okay, I'm just telling you it's going to be this linear profile here, and we won't worry about it at all. Okay, now let's do full diffusion theory, because as you'll see, this is an approximation that is not valid for dopant. So diffusion theory, let's pull out our thin box again. Okay, so this is at x, and this is at x plus dx. And we're going to have a flux of x. Now remember, F here is dopant atoms per unit area per unit time. So we're going to have a flux at x, and we're going to have a flux at x plus dx. And they're not going to be equal to each other. All right. So first of all, for oxidation, we approximate that f of x plus x dx is equal to f of x. Sorry, I ran out of board here. Let me rewrite that. For oxidation, we approximated that f of x is equal to f of x plus dx. Yeah, that got on the picture. Right? Because, okay, remember F is negative d dc dx. Okay, it's the slope. And for oxidation, we approximated that the slope at any given time is the same. But for diffusion, for dopant diffusion, f of x is not equal to f of x plus dx. Which you can see, you know, what I drew here, the slope is not the same. Now, I'm stating things and I'm not stating why. And let's go through the analysis and worry about why later. So let's go through the analysis. So we're saying there's a flux going into the box. And so we can write down, okay, remember flux here is the dopant atoms per unit area to unit time. Okay, so we can write down that f of x minus f of x plus dx. Now what is that? Okay, that's the difference between what is going in the box and what's going out. All right, so think about it. That is the atoms, the dopant atoms per unit time per unit area delta. Okay, because it's different, there's more. Okay, let's say f of x is bigger than f of x. Okay, so it's the opposite, really, of course. Let's say, you know, we were treating some arbitrary situation where f of x were bigger than f of x plus dx. Okay, it's just like a tank of water or something like that. If there's more going in than is going out, then there's going to be an increase of what's ever inside the box. And so what we can do now is that we can divide this by dx on both sides. And then this is volume. So we can write then, and this, and I'll scrunch it down over here, you know what this is. This is a derivative. Right? That's the change in f with x. And so we can write down then that df dx is equal to, and I'll put the minus sign over here. Now what is d delta, dopant atoms per unit volume per unit time? Well, the dopant atoms per unit volume, that's n. So this is equal to dn dt. because N is the dopant atoms per unit volume. So this is delta, dopant atoms per unit volume, per unit time, dN dt. Get it? It's pretty simple, really. And so this is the diffusion equation. And we can go further because we know, I wrote it down over here, all right, and before we go further, all right, you guys remember this from math, right? I got two variables now, x and t, so I got to make these partials, which doesn't need, don't worry about it. I mean, it's just what it is. And F, right, what is the flux? Minus d, n dx, just like it was dc dx over there. So I can plug that in here, and the minus signs cancel. So I get d times the partial squared of n with respect to x squared is equal to the partial of n with respect to time. And that's the full diffusion equation. Okay, and what does it say? Well, what it's saying is that, okay, if n versus x is not linear, it's some curve, nonlinear curve, then at any given point in space, there has to be a change in n with respect to time. And of course, that's exactly what's happening, right? Okay, this is oops, the other way around. This is time, right? So at time 1, it's this point, and so at time 1, n is that, and at time 2, n is that. And so dn dt is equal to the difference in this, is equal to the second derivative of this curve here. All right, now let's get back to oxidation for just a second, because we didn't do that, okay? I just told you it was a straight line. And the reality is, okay, it's not exactly, because, of course, at a given point, all right, so this is t, this is t, and this is t plus delta t, for example. C is changing with respect to time. It's just we approximate for oxidation that dc dt is approximately 0, meaning things are happening very slowly, is the idea. And in terms of the, and you kind of get that a little bit, that because, I mean, look at what I've drawn here. These two curves at different times are very close to each other, whereas these two curves here are very much farther apart. So in diffusion, at any given point in space, the n is changing very fast compared to an oxidation where it's changing very slow. And so for oxidation, we make this approximation that dc dt is small, about 0. And so that results in the second derivative with respect to x being 0, which means it's linear. So I just wanted to point out to you that, okay, we could have used this for oxidation. Of course, we would put C there and Z. But we didn't, okay? And I essentially didn't even introduce to you. I just sort of said, okay, I'm not going to explain to you why, but it's a straight line. Which straight lines are always nice. It's always, it's going down as, as it goes into the wafer, that the concentration is higher at the surface, okay? And straight lines are, the simplest way to draw that. That's something going down a straight line. So that's what we did, okay? But now when we get to dopant diffusion, we can't do that, okay? It's not true. For dopant diffusion, we can't make this approximation. You know, we can't make the approximation that dm dt is equal to 0. We can't make that. So for dopant diffusion, we have to use the full equation. All right, well, that's not so horrible. It's nice for oxidation that we can use a straight line, but for dopant diffusion, we can't. All right, so now let's do dopant diffusion. And for dopant diffusion, I'll redraw my thing. Okay, this is now X for some strange reason. This is N. This is the wafer surface at X equals 0. And that was the other difference. For oxidation, we have C sub S. For oxidation, or for dopant diffusion, we have N sub 0, I think. Or is it the other way around? I forget. Okay, well, you get the idea. I'm sorry if I used 0 somewhere else, but I'll use N sub S here. It's the same thing, N sub 0 at the surface, N sub S at the surface. And now we want to know what the profile is. And I kind of indicated it was something curvy, which it is because it's going to be curvy because we can't approximate that dm dt is 0. So this is, you know, a differential equation. And what's worse, it's a partial differential equation. It has 2 independent variables. And the boundary conditions, do I need to write out boundary conditions? I'll write out boundary conditions. The boundary conditions are, okay, the first one's easy. Well, actually, the first one is kind of complicated, as they're written in the notes here. So N for t equals 0 is, okay, so what's t equals 0? That's when you turn the dopant gas on. So before t equals 0, there's no dopant gas. So I'm going to write it this way. It's 0. All right. But except that, so this is 0 for x is greater than 0, but it's ns for x equal to 0. Now that sounds pretty funny, and it actually is a funny boundary condition because it's saying that, okay, I turn on the dopant gas, turn on at t equals 0. I turn on the dopant gas and instantaneously the dopant at the surface, the concentration at the surface of the wafer goes up to N sub S. But it's 0 everywhere else because nothing has happened yet. And so it kind of looks like that. All right, this is t equals 0. It's a funny boundary condition. It has to be N sub S at x equals 0, and it has to be 0 everywhere else. So that's pretty funny. All right, the next boundary condition is at n for any t, n of x equals 0 is equal to N sub S for all t. Okay, so my next boundary condition is that now I'm going to let time go on, and it's always N sub S at the surface. So that's kind of easy to understand. Okay, it's determined by the concentration of dopant atoms in the gas, and so that keeps the concentration or the density of dopant atoms at the surface fixed at n sub s. And the next boundary condition is also pretty easy to understand. As x goes to infinity for any time, it has to be 0 for all time. And it turns out that if you plug those into that equation, all right, the nice thing here is that someone has done this for you. The solution, so you plug those boundary conditions into that differential equation and it spits out a solution that x, n of x and t, so there's two independent variables, space and time, is equal to n sub s times 1 minus what's called the error function of x over 2 to the square root of dt. So, and that's sometimes called the complementary error function. Complementary error function is equal to 1 minus the error function. So those nice scientists or physicists or whoever have nicely worked out. They've, some mathematician, saw this, saw these conditions, and go, okay, I can give you an equation. There it is. Now, of course, ERF doesn't really, sound that fun. It's not very intuitive, which is why you're doing problem 1 of the homework. Oh, by the way, homework 6. I'll say it in the announcement, is due Sunday. And so when you, now let's look at ERF, because ERF is well known. So ERF, and I'm going to put x prime, where x prime is equal to x over 2 to the square root of dt. Okay, we'll just do that. We'll fix this up in a little bit. Looks like this. Okay. Oops. So it starts from 0, and it goes up kind of linearly, and then it curves over, and then it asymptotes to 1. So then you go over here, and what this looks like then is 1 minus that. So of course 1 minus 0 is 1, and it's ns at the surface, which was our first boundary condition. And then it basically goes down kind of like a straight line. All right, and at x equals infinity, right, it's equal to 1, depending on time. And so it kind of does something like that, increasing time. So that's not so bad. Okay, so it's just this function. And it's something you have to deal with, and you have to look up in a table what x of something is, or what ERF of something is. Now, we're going to finish there for today, because you have enough information that, yeah, we'll finish there for today, because you have enough information to get started on this, and this is probably a good place to have a little break. And the last thing I'm going to do is this, okay? I'm going to define that as x over L. So I'm defining L as 2 times the square root of dt, and this actually has a term, it's the diffusion length. So basically, L goes up as the square root of time. And we'll end there for today, and you have enough information to get started on homework 6. Homework 6 is due Sunday. which I'll discuss in the announcement. Okay, so that's it for today, and I'll talk to you tomorrow in class.